Okay, now let's take a look at some further examples. Once we know how to calculate the electric field of infinite long uniformly charged line, it is quite simple to extend it into the electric field of a uniform cylinder filled uniformly with a certain charge density rho. You know, this is a three-dimensional object, and we didn't even attempt to calculate the electric field produced by such an infinite long uniform cylinder in the previous chapter because the integral would be too much to handle. However, the method that we're going to use to solve this problem is very much the same as the one we used to solve the previous one, where the cylinder was just replaced by a single infinite long line. Because even though this is a finite size cylinder of radius r, you still have the same type of symmetry, right? Cylindrical symmetry. So for example, if you want to calculate the electric field at this point, a point P, outside the cylinder, how do you capture the symmetry of the cylinder by drawing an appropriate Gaussian surface? Well, obviously what you would do is the same as before. You draw a cylindrical Gaussian surface, right? A cylindrical Gaussian surface like this. It passes through point P, and it extends downwards like this with a certain length L, just like before. And then the argument follows the same as the previous example. You notice that the electric field only penetrates the side of the cylinder. It doesn't go through the top and bottom. So you have, through this Gaussian surface, you have E dot dA equals, first of all, it's only the side that contributes E dot dA. And then for the side, first of all, E and dA are in the same direction. They're both radiate outwards. And secondly, E has the same magnitude. So I can write this as E and then dA. For the side, this is simply just the same as before, E times 2 pi r L. L being the length of the cylinder. And this equals to what? It equals to the charge enclosed divided by epsilon naught. Is the charge from here to there, okay? So we can easily calculate that. It is just lambda times L over epsilon naught. And lambda can be expressed in terms of rho if you want to, because lambda is the charge per unit length. Now, you look at the unit length. What is the total amount of charge enclosed? Well, the volume of a cylinder of unit length and radius r would be pi r squared times 1 unit, right? That's the volume. Volume times density times the density rho, what do you get? You will get the charge enclosed by the cylinder per unit length. And this, by definition, is lambda. Okay? So this is equal to rho pi r squared L over epsilon naught. And now we can calculate, we can go ahead and solve E. E outside equals what? You move that 2 pi r down here. Okay, pi and pi cancels. It's rho r squared, L and L cancels, 2 epsilon naught r. That is the electric field outside, and it's radially outward as far as the direction is concerned. So it's pretty much the same as the previous example. Now the difference is, what if we dig a hole into the cylinder, say a point here, with a radius small r from here to there, that is less than the radius of the cylinder. Now, you can still look at the symmetry of the problem. You still draw a cylinder, but this cylinder is smaller, okay, from here to there, right? It does not quite capture the entire amount of charge between here and there. It captures part of it. So how much does it capture? Well, it captures the electric charge enclosed in this region. And how does that compare with the total amount of electric charge contained in that region? Well, these two regions are both cylindrical with the same length, which is L. So as far as the volume is concerned, the ratio of the smaller volume over the larger volume is just a ratio of the cross-sectional areas, okay? The cross-sectional areas, pi small r squared divided by pi big R squared. So the charge enclosed, in this case, the charge enclosed, Q enclosed, for this region would be the total charge enclosed, which is which is lambda L, right? Which is lambda L, or pi r squared L times rho. So it's pi r squared L times rho multiplied by a factor. What factor? This area over that area. Okay, so it's pi small r squared over pi big R squared. And you cross up pi big R squared, you get pi small r squared L times rho. But you know, this actually is obvious. You don't even have to go through this this derivation, because after all, pi small r squared times L, isn't that just the cylinder, the volume of this smaller cylinder, right? You multiply this by the density, charge density. Don't you get the charge enclosed? This is the charge enclosed by the smaller cylinder, which is our new Gaussian surface. So from that, we can calculate E. Okay, what is E equal to now? Well, it is the same you solve for E from here. Lambda L is now replaced by this new amount of charge, right? Because that's a new charge enclosed. So it's pi r squared L rho. And you divide this by epsilon naught here. And you also divide this by 2 pi RL. So, okay, 2 pi RL. So let's cancel out some common factors, L and L, pi and pi. And you will get our new expression. The new expression for the electric field inside this Gaussian cylinder is rho r over 2 epsilon naught big R squared. Okay, this is for r less or equal to big R, and that one is for r greater or equal to big R. And you'll notice what happens right on the surface of the cylinder. These two expressions, as expected, will give you the same exact result. So there is no discontinuity expected on the surface for the electric field. You can see here, when big R equals small r, right, these two expressions will give the same result when take big R equals small r. Both will be equal to rho times big R over 2 epsilon naught. So if you were to plot the electric field for a uniformly charged cylinder, here's the radius of the cylinder, here's the electric field, and here is the radius r. Outside the cylinder, it goes like 1 over r, just like the case of an infinite long line. In fact, you cannot tell if this is just a thin line or if it's a finite size cylinder. If you're outside the cylinder, you will get the same exact electric field. But once you're inside, you see, just like the case of uniformly charged sphere, you're going to get a linear electric field. You know, it goes like r to the first power, so it goes like this. Okay, linear, and then 1 over r. That is the case of an infinite long uniformly charged cylinder. We are able to find the electric field without too much hassle in our calculation. So these were two examples of cylindrical symmetry. So now we have one type of symmetry left, and what would that be? That would be planar symmetry. Okay, so the symmetry in the shape of a plane. Planar symmetry. So the next example, example number 5. I have an infinitely large, uniformly charged plane. What is the electric field produced by this plane? Say you have a plane like this. Okay, it's uniformly charged to charge density rho. Sigma. Sigma is the surface charge density, charge per unit area. Now you know we calculated that example before in the previous chapter. What did we do? We started with a ring, uniformly charged ring. We calculate electric field outside the ring, and then we integrate a whole bunch of rings to get what do you get? We get a solid disk, right? And then we took the radius of disk to infinity, we get an infinitely large plane. So we went through several steps of calculation. We integrated twice. Okay, but now you can see that with our new weapon, the Gauss's law, we can solve this problem with much greater efficiency. Once again, the key here is to capture the symmetry with the right shape of Gaussian surface. In this case, now let me draw the electric field like this. First of all, I'm going to turn this plane like this. Okay, so I'm going to turn this plane so it's a side view. So I'm looking at it from this angle, like this. Okay, so it's a plane like this. It's got positive charges uniformly distributed everywhere. All right. What kind of electric field lines can I expect for distribution like that? Well, it's quite obvious that by symmetry, the electric field should be perpendicular to the plane both above and below the plane. And also the symmetry tells us that if you draw a line that is parallel to the plane itself, or a plane, another plane that's parallel to the plane containing the charge itself, then anywhere on that same plane, the electric field should be the same, right? Should have the same magnitude, right? Because of the symmetry. So, what kind of Gaussian surface should I draw this time? Well, it's obvious that this time I'm going to draw a Gaussian surface in the shape of a box. Okay, it's a box like this. Here's the top, here's the bottom. I want to make the top and bottom parallel to the plane containing the charge, because that way everywhere on the top and the bottom of that box, the electric field has the same magnitude in the same direction. Okay, and in order to simplify matters, I'm going to deliberately make this distance equal that distance. In other words, this distance equal that distance, so that the electric field here, E, and that E, will have the same magnitude as well. The only difference between the electric, that this surface and that surface, is that they have opposite directions. Okay, they have opposite directions. So let me enclose the cylinder like this, enclose the box like this. So here's the top surface, here's the bottom surface, and here is the side. Now this time, you know the electric field does not go through the side, okay? Because the electric field is always like this or like that. They don't go through the side, they only go through the top and the bottom of that box. And because of the shape of the box, the top area and the bottom area are equal to each other, right? Let's say the area here is A, the area there is also equal to A. What is the flux going through the top? Well, you have a uniform electric field everywhere on the surface of area A, and so the flux is just E times A going through the top surface, right? E times A. And same E times A going through the bottom surface, because E has the same magnitude and A is the same here and there. So you double that, 2EA. That is the flux going through both the top and the bottom. And there is no flux going through the side because the electric field lines are parallel to the surface on the side. So that is it. That is all the flux there is going through this Gaussian box. Fine. Just equal to that, okay? But according to Gauss's law, that should be equal to what? The total charge enclosed by this Gaussian box divided by epsilon naught. Okay? How much charge did we enclose? That much charge. In other words, that much charge. Now, that area is the same as A. This A, that A. If the charge per unit area on the sheet is sigma, how much charge did you enclose? Should be sigma times the area A, right? So that is charge enclosed over epsilon naught, and that is just sigma A over epsilon naught. Okay, you see A and A cancels neatly. You move that 2 down, you get yourself the final expression. It was equal to sigma over 2 epsilon naught. Okay, this in fact is a familiar result that we obtained before. In fact, if you rewrite this as 1 over 4 pi epsilon naught, which is k, of course, and then you have a 2 pi, okay, sigma. But that's the same thing, right? That's the same thing. That's just k. So that is 2 pi ke sigma. Now go back to the previous chapter in our notes. You will find that we got the same result before. We took a cylinder, we took a disk, and we calculated the electric field on the axis of a disk, and then we took the area of the disk to infinity. We got that same result. But look at how simple our calculation is, right? It's much more efficient than a straight integration, which involves a lot more work. So that is our third type of symmetry, planar symmetry. Now, this is just an infinitely thin plane, but you don't have to have the infinitely thin plane. You can have a finite thickness. As long as the charge density is uniform and the sheet is infinitely large, you will not break the symmetry of the problem. So naturally, we can extend this to our next example. You have a sheet. This sheet is oriented like that, okay? It's oriented, perpendicular to this piece of paper. It's like this. But this time it's got a finite thickness. The thickness between here and there is not 0, unlike before. And we fill this infinitely large sheet with a uniform charge density rho. Okay? What I want to know is, what is the electric field everywhere in space? Well, obviously, there is a plane in the middle. This plane in the middle, breaks the space into the left half and the right half, and everything should be reflectively symmetrical about this plane. Alright? For example, everything to the right of this plane, the electric field should be perpendicular to the plane and going to the right, assuming the rule is positive, of course. Everything to the left, the electric should do this, should behave like this. Okay, that makes sense. Now, if you look at a point outside this sheet, here or there, just like in the previous two cases, you will find that you just recover the same result as before, as if the sheet were crushed into a plane right here in the middle. Okay, so there's nothing new if you're outside. You cannot tell how thick the sheet is. If you're outside, the electric field would just be the same as if the sheet is infinitely narrow. On the other hand, if you dig a hole, okay, suppose you dig a hole perpendicular to the sheet, and you put an electron inside, then what happens? Well, you can figure out the electric field at that point, at the location of the electric field. Let's call this distance x. Okay, x is measured from the center of the sheet. The electric field inside, at the location x, is not quite the same as before, because even though we have the same symmetry, it does not include the same amount of charge. Let us draw a Gaussian surface like that, just like before, okay, in the form of a box. See, in the form of a box. Okay, the area is A and area is A. Now, to reflect the symmetry, I'm going to make this is equal to that distance. Both are equal to x. All right, so the thickness is, the height of the box is 2x. The orientation of the electric field, like this, and then over there is like that, right? And everywhere on this surface, the electric field has the same magnitude. Everywhere over there has the same magnitude. So just like before, the electric flux through this smaller Gaussian cylinder is 2 times E times A. Okay? 2 times E times A, just like the previous case. But it equals Q enclosed over epsilon naught. And this Q enclosed, I have to recalculate it. It is the charge enclosed by this smaller cylinder. This smaller cylinder, the charge density is rho, but the volume is area A times the thickness, I'm sorry, times the height of the cylinder, which is 2x. You see, 2x. Okay, and you divide this by epsilon naught. Now, careful. You see, phi depends on E, now depends on x. Okay, A and A cancels. You move that, you cancel 2 with that 2, and you get yourself the electric field inside the sheet, and that equals to rho over epsilon naught times x. Right? That's E. It is no longer uniform. Okay, the field inside the sheet is not uniform. The field outside the sheet is uniform. What's interesting about this situation is that if you were to dig a tunnel and put an electron there, this electron would then experience a force which is linearly proportional to that distance x, right? F, the force exerted on this electron, is the charge of the electron negative E times the electric field, and then you know this negative E rho over epsilon naught times x. But this, as you recall from physics 1b, is a linear restoring force, right? It's negative constant times x, and that constant, let me call it K effective. It's like an effective spring constant. So I'm going to call this negative K effective x. Under the influence of such a force, what kind of motion will this electron execute? Well, obviously, it's going to be simple harmonic motion, right? Simple harmonic motion. And the effective spring constant is E rho over epsilon naught. And you recall from the knowledge of physics 1b, you're going to get a simple harmonic oscillation, and the period of that simple harmonic oscillation t is 2 pi times the square root of m over K effective. M is the mass of the electron, so we can calculate that easily. M divided by K effective, so that is epsilon naught over E over rho. You will get a simple harmonic motion. You put an electron in there. Okay, now take a look at this expression. This is for the electric field inside the sheet, all the way to the surface. Okay, from our previous experience, we know that that should match the expression for the electric field outside the surface, at the surface itself. So in other words, there is no discontinuity on the surface, because right now on the surface there is no sigma, there is no two-dimensional charge distribution. Is that right? Well, when x equals this length, which I call d, okay, then you get rho times d divided by epsilon naught, right? That should match the electric field outside. How much was that equal to? That was equal to sigma over 2 epsilon naught. What's sigma? Sigma is the charge per unit area. So you take a unit area like this, how much total charge is enclosed? So let's see how much sigma is equal to. Sigma in our case, okay, the total amount of charge enclosed by unit cross-sectional area. For unit cross-sectional area, okay, for unit cross-sectional area, the volume would be the unit cross-sectional area, which is 1, times the thickness of the sheet, which is 2d, right? Which is 2d. So that is the volume. Take volume times the density. It's three-dimensional charge density. Don't you get the total amount of charge enclosed by this unit cross-section area? And that, by definition, is rho. So rho is 2d rho. I'm sorry, sigma is 2d rho. Okay, so given that E outside is equal to sigma over 2 epsilon naught, with this I can rewrite it as 2d rho over 2 epsilon naught. Cross out that 2. That is d times rho over epsilon naught. You see, we get the same exact expression if I take x equals d, right? We go right to the surface. So the electric field, if I were to plot the electric field, okay, using x equal to 0 at the center right here, then this is d, this is negative d. Okay, so inside the electric field goes like constant times x, so it goes like this. Okay, it goes like this. And outside, the electric field reduces to a simple constant like that, right? So this is how the electric field behaves for such a system. Again, there is no discontinuity at the surface because there is no sigma right on the surface.